All right, everybody. So, chapter 2, the chemical context of life. This is our basic chemistry unit, okay? So, the first thing I want to show you is the periodic table of elements, and we're going to be going through what a period in a group is, right? So, the periods are the horizontal rows, okay? And then groups are vertical, and we're going to be looking at some of the different characteristics of this, okay? But if you Google this, you can actually click on this. If you Google this, the periodic table of elements in pictures and words, okay, it's an interactive periodic table, and you can click on it, and it'll bring up all the different types of elements. So I just wanted to show you that, okay? So when we look at the types of elements that are found in the earth, okay, versus the elements that are found in our body, you can just take a moment to look at this chart here. When you analyze this graph, okay, so what do you see? So hopefully you said schnapps. Okay, so schnapps are the main elements that make up our body. And so let's see if you can remember what they stand for. That's right, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are what make up 95% of our body weight. All right, so next we want to talk about the parts of an atom. Okay, so the way I remember it is something called the atom story. So we're going to learn another one of those hand jives. So I'm going to just get a moment, get myself set up. I'm also going to turn off my text message alerts. So let me just move my little face here. Oops. Make myself big. Okay, and so here is the atom story. Okay, so atoms are made of protons, right, positive, neutrons, and electrons. Electrons are negatively charged. So atoms are made of protons, neutrons, and electrons. Protons and neutrons are in the nucleus, atomic mass. Electrons are orbiting in energy levels. Lowest energy level holds 2, then 2, 8, 1832, then 8, 8, 8 is great octet rule. All right, so now we know how to fill those orbital shells, and we know our energy levels. Okay, so let's do that one from the top. So atoms are made of protons, neutrons, and electrons. Protons and neutrons are in the nucleus, atomic mass. Electrons are orbiting in energy levels. What is the lowest energy level? Well, it's 2, 2, 8, 1832, 8, 8, 8 is great octet rule. All right. So let me move myself down. And so when we learn about atoms, okay, we're going to see that they're always wanting to become stable. Okay, so they can do it if one of two ways. They can either fill up their outermost energy level, and that's super stable, or they can fill it up to 8, and that's referring to the octet rule. Okay, and so that's good enough for now. We'll put a pin in that, and then we're going to move on to atomic structure. Okay, so let's first fill in your notes here. So for atomic structure, I want you to put the smallest part of an element that displays the property of that element. Okay, so we're looking at an atom. It's the smallest part of that element that displays the properties of that element. So there's nothing magical about those words. You're never going to be asked a question like that. But you just need to understand that an atom, right, is the smallest part of that element that still has the properties of that element. Okay. And so the properties of an atom is really dictated by its atomic number, which by definition is always equal to the number of protons. So we had for mass number, right, protons plus neutrons, atomic mass, but atomic number is the number of protons. Okay, so atomic number is the number of protons. Now, in a neutral atom, however many protons you have, you're going to have the same. So, however many protons, you're going to have the same number of electrons. That means it would be a neutral charge. Okay, But if you have more electrons than you do protons, right, you would have more negative charge on the atom. And vice versa. If you have more positive charge than you do negative charge, then you would have what is called an ion, okay? So those would not be neutral atoms. Ions mean they either have a positive or a negative charge, okay? So now we're going to talk about what happens when you don't vary the number of and change the charge, but what happens when you change the number of neutrons. Okay, so let's just take a look at this chart. This is just sort of a summary of those subatomic particles and the charges that they have, okay? So we know proton, positive charge, is located in the nucleus. Neutron, no charge, has the same atomic mass as a proton and also located in the nucleus. And then we have electrons, which are negatively charged, and they are located in those electron shells, okay? So let's take a look at the element helium, okay? So if we look at the mass number, this is indicating what? Protons plus neutrons in the nucleus, mass number. So this is our number of protons and neutrons versus we look at the atomic number. This is just telling us how many protons are in the nucleus, okay? So now let's look at lithium. So lithium, it has an atomic number of 3, so we know that it has 3 protons in the nucleus. But then we see 7, okay? So we know mass number, protons plus neutrons in the nucleus is our mass number. So we see 7. So that means there must be not 3 neutrons, but 4 neutrons in this nucleus. And so what could that possibly mean? This must mean that this is an isotope of lithium. So now let's remind ourselves what an isotope is. Okay, before we move into isotopes, let's just kind of also talk about, so if this lithium has 3 protons, that means it also has 3 electrons. Okay, so if I have the same number of protons, I should have the same number of electrons, okay, in a neutral atom. So how am I going to know which energy level to fill up to with these electrons? Okay, so remember the rule. So it goes for energy levels, it goes 2, 8, 1832, right? So how many can I fit in the first energy level? I can fit 2. But I have a third electron, right? So that's going to go up into the next energy level. Now, when you think about the next energy level, how many can that next energy level hold? It can hold 8, right? But it only has 1 electron in that next energy level, right? So is this lithium going to be stable, or is this going to be a really reactive atom, right? And so hopefully you said reactive, because it only has 1 valence electron, and that is going to be in 1 valence electron in its outermost shell. It wants to be at 8, right? So it's down 7. So what are the odds that it's going to find 7 more electrons, steal them, right? That's not high. What's likely going to happen is it's going to try to ditch its electron, right? Share it with another atom. So we need to understand the chemistry right behind this, because then we can understand how chemicals will behave and respond, interact with each other, and then we can make predictions, and that will help us understand life quite a bit, okay? So we're going to hit that again, but now let's move into isotopes, okay? So what's an isotope? So the next one in your notes, remember, it's a variance in the number of neutrons, right? So atoms of the same element, but they vary in their number of neutrons. So you can put that down in your notes. Pause if you need a little bit more time. Okay. So atoms of the same element that differ in their number of neutrons, that is an isotope. Oops. Oop. Okay. So if you look at these isotopes, these are all isotopes of helium. Okay, so what do they have in common? Well, so hopefully you said they all have the same number of protons, okay? can see those 2 proton positive charges in all of them. So what is different and varying here are the number of neutrons in their nucleus. Okay, so for this one, we'll use helium-8, right? It has 2 protons in the nucleus and 1, 2, 3, 4, 5, 6 neutrons in the nucleus. Okay. So essentially, we use isotopes in medicine to help us to trace and find how the body is using up some of the trace markers, which are made of isotopes. And we can find that by seeing how quickly they're trying to shake off those extra neutrons in their nucleus. Okay, and so you can go ahead and read this, but this is the use of radioactive isotopes and those neutrons trying to shake themselves off to try to become a stable nucleus again, as opposed to having way more neutrons than there are protons. We use this to help us find things like cancer. We can find kidney function and how kidney function is going in the body by using these radioactive tracers to see how they're reacting with organic molecules in our body. Okay, so it can be used in lots and lots of different ways. All right, so now let's look at this periodic table. This is a very simplified periodic table, but we're going to remember that the periods are the horizontal rows and the groups are our vertical rows. Okay, so let's start with, how about we start with helium? Okay, so we see that helium, its atomic number is 2. So that means that it has what? Its mass is 4 and its atomic number is 2. So we know that it has 2 protons and 2 neutrons. All right, so but now let's look at hydrogen. So hydrogen's sort of an interesting one, right? So we see the atomic number is 1, number of neutrons, and the atomic mass is 1.008. So what's that business about, right? Shouldn't there be a 2? Because then shouldn't there be a neutron? So no, in hydrogen, there is no neutron. So make sure that you're clear on that, right? If this is indicating hydrogen only has the proton in the nucleus, okay? So I want to just talk about what's this business with all of the, why aren't these whole numbers? Why is carbon 12.01 and nitrogen is 14.01? Well, essentially, these atomic mass, proton plus neutron in the nucleus, atomic mass, they are decimals because what they're doing is taking the average of all of the isotopes of that element, all the different versions of that element, and their abundance on Earth. Okay, so that is why you're seeing these variable atomic masses. Okay, it's an average of all of the isotopes. Okay, so let's see here. So let's start by looking at groups and seeing where we can find things in common, okay? So let's see what is similar, what are the commonalities between lithium and hydrogen, okay? So if we think about how we fill our orbital shells, okay? So the first one is 2. So for hydrogen, it only has 1 electron that would be in that orbital shell because it has 1 proton, so it should have 1 electron. So that means its valence electron, the electron in its most outer shell, is 1. Let's try with lithium. Okay, so lithium has 3 protons, so it has 3 electrons. So if we're trying to fill those shells, we fill it 2, then we could fill 8. But so we filled 2, now we add 1 more, we're at 3. And that's it. So we have, again, another orbital shell where its number of valence electrons is just 1, just like hydrogen. And that theme could go all the way through this group, okay? So now let's look at what we see in terms of similarities between periods. Before we move on to groups, so let's just confirm then. So if we use this as a tool to know how the elements will be organized on the periodic table for how we can make predictions about how elements are going to behave, right? So we know that everything in this first group is going to have one valence electron in its outermost shell. Everything in this group is going to have two valence electrons and three, and so on and so forth. Okay, the only ones that have eight, right? Octet rule, eight is great. Eight valence electrons in its outermost shell are these guys, are noble gases. Okay, and so these guys behave also in very similar ways. And because their outermost energy level is completely full, they don't really need to react with other elements to be stable. Okay, they're happy all by themselves. They're not trying to have reactions in the same way that, like, if we see oxygen, right? Oxygen would have two in its inner shell and then six in its outermost shell, right? It's just two away from that full octet. So it really, really, really wants to be happy and have a full outer shell. So it's going to do what it can to steal electrons to try to be a complete octet, okay? And to make sure that energy level is full. Okay, versus if we look at helium, right, it's a great candidate for another element to try to steal its outer electron to make it happy. Okay, and it could, by bonding, and it could make hydrogen happy because it has just one electron floating around in that orbital, right? It wants to be happy as well. It wants to be a full octet, full energy level. Okay, so let's see. Okay, so what is the purpose of the periods, right? So the periods are really just telling you what energy level your electrons are residing in. Okay, so for lithium, right, they'll be residing in the first energy level is filled. So their electrons are residing in the second energy level. Okay, if we move on down for sodium, right, that would be they have filled the first and second energy level, and now they're into the third energy level. So you can see that where an element resides on the periodic table helps you make predictions and determine how it will react with other elements based on really what number of valence electrons that element has. Okay, so if you look at your notes, the only thing that you need to add to your notes on there that I left blank is on groups. Okay, the vertical columns are arranged by number of valence electrons, how many valence electrons you have. So everybody in this group 1, right, has one valence electron, versus periods are the horizontal rows, and that is equal to the electron's energy level, right? So it's either 2, 8, 18, 32. And we don't need to worry right now about the transition metals or elements, anything like that. We just want to know, why does an element react in the way that it does? And how do we know, so that we can really determine what sorts of molecules it's going to form and the molecular behavior. And if we know that, then we can understand how perhaps the molecules that build our cells and build our organelles, how they behave, and thereby understand our biology more. Okay. All right, so the next slide is all about these energy levels, right? So essentially, each level contains a certain number of orbitals, and there's a certain number of electrons that we can place into those orbitals. 2, 8, 1832, and then we have our octet rule, 8. 8 is great, okay? All right, so let's talk about how electrons go up and down between energy levels, okay? So electrons jumping to a higher energy level means that they received energy in some way, and so their electrons got excited, gained energy, jumped up to another energy level, and as they come back down, they release some heat. Okay, so we're going to specifically talk about this with photosynthesis, but we could also talk about it when we think about why surfaces get hot. Okay, so let's think about you park a dark colored car, a black car in a parking lot. Okay, that black color is going to absorb a lot of sunlight. So when you put your hand on the car, why does it feel hot? Well, it has to do with the atoms in the paint of the car. The electrons are so excited that they are expending heat. So let's think about it. The sun, it releases energy in the form of photons. Okay, those photons are hitting the electrons that are orbiting around, and when that photon excites the electron, gives it energy, it jumps from one energy level up to the next one. Okay, then its potential energy is much higher, so it's going to come back down to a normal energy level, and when it does, it releases heat. And that's why you put your hand on the car, it's hot. Okay. Okay. So remember that how an element is going to act is based on the number of electrons in its outermost energy level. Okay. So here, these are our protons. Okay. And then these are our neutrons. Okay. And the key is the number of electrons in the outermost shell will show us how much it will react with other atoms. Okay. And so we have that right here. So this outermost shell has 1, 2, 3, 4, 5 electrons in its outermost shell. It always wants to be at 8, then it's happy and stable. And so this is going to want to fill with 3 more electrons so that it's happy and its octet is filled. Okay, and so we'll be able to then determine how this atom might react with other atoms based just solely on its number of valence electrons. Okay, so just to sort of summarize this and to make sure that you see how it connects to where it fits the need for the College Board's requirements about chemistry. Okay, so this actually is going to be supporting in your unit HyperDoc 1.2. Okay, and really what this is saying is that an electron, as it absorbs energy, it boosts it up to a higher energy level where it has more potential energy. Okay. So let's look at these, a handful of these elements here, these atoms, and let's see, just based on its number of valence electrons, how we think it's going to act. Okay, so first we'll see hydrogen. Hydrogen has 1 electron in its valence shell, which means that it's highly reactive. It's going to probably react with another element to get stable. Okay, so then same thing with carbon here. Okay, we have carbon has 4 valence electrons in its outermost shell, and it wants 8. And so this is carbon, because of its 4 electrons in its outermost shell, it makes it one of the most bonded to elements on the periodic table. The properties that are part of carbon, because of the nature of its valence shell, makes it so that it's one of the most prominent atoms in our body. Okay, and so let's take a look at oxygen. Okay, oxygen is highly reactive because it has 6 valence electrons in its outermost shell. It wants 8. And so it's going to be a highly reactive atom. It's going to try to do whatever it can to either steal or share with another atom so it can have a full octet in its outermost shell. So really, the number of electrons in the outermost shell determines its reactivity. Okay, so does an atom need an electron to become stable, or does it want to ditch an electron that will help it become more stable? Okay, so that will be its motivation behind behind bonding. Okay, so then let's move into bonding. So there's 2 types of bonds. There's actually more than 2 types of bonds, but we're just going to start here with covalent versus ionic bonds. Okay, so let's begin with ionic. Okay, so in ionic bonding, you are actually having the transfer of an electron. So in doing so, by transferring, I'm going to move my little face over here. So in transferring an electron, we know that electrons are negatively charged. So if an atom, let's say it's an atom of helium, okay, so 2 protons and 2 electrons. So when it loses its electron and it's donated to another atom, that means that that helium now has a positive charge, extra positive, because it has 2 protons still in the nucleus, but only 1 electron in its outermost shell. Versus the atom that just was given this electron, it's going to be more negative now. It has an extra electron donated to it. So this would be called an ionic bond. So the negative ion would be the one that has an abundance of electrons. It has more electrons than it does protons, versus the positive ion, which has a more positive charge. It has less electrons because it was donated. Okay, so then we move to covalent bonds. Okay, so in a covalent bond, the electrons are not donated, right? They instead are shared. So in covalent bonds, it is the sharing of electrons. So as we can see, we have, this is hydrogen and hydrogen, right? We have our positive proton, our 1 valence shell electron, okay? So hydrogen, it has a tendency to want to bond to itself to stabilize. So here we see this is now hydrogen gas. We have the sharing of these 2 electrons evenly between the 2 hydrogen atoms, okay? But they are sharing these electrons together. Okay, so they're not trying to ditch any electrons in a covalent bond. In a covalent bond, they're trying to share to be happy, to stabilize, okay? Okay, so for our ionic bonding, really the rule here is that opposites attract, versus covalent bonding, we're seeing the sharing of electrons. Okay, so in your notes, okay, it says, why do molecules bond? You want to say for stability. So they're trying to bond to stabilize, right? They want to have a complete set in their outermost shell. They want to be that happy octet. Okay, so I also want to review one more time ions versus isotopes. Okay, so let me get my face out of the way. Okay, so ions are when an atom gains or loses an electron, resulting in a positive or a negative charge. Okay, versus an isotope, which is where the number of neutrons in the nucleus is variable. So I like to think of isotopes the way I think about apples, okay? So if I give you a Granny Smith apple and I give you a Pink Lady apple, you're going to tell me these are 2 different versions of apples, but they're both apples. Isotopes are the same way. If I have carbon 12 or I have carbon 13 or I have carbon 14, they're all still carbon, but they're different versions or variances of carbon. Okay, so all right, so let's start with ionic bonding. So what do ionic bonds start with? Okay, they start with ions. So let's take a look at some of the ions here on this page, okay? So we could use, let's take a look at our calcium, okay? So this calcium ion was negatively charged, okay? Okay, so I think that maybe you guys can relate, because when you're filming your Friday flip, something weird happens with my brain when I'm recording and I get sort of tunnel vision. So, okay, that's not calcium, that's carbon. Let's talk about the calcium, okay? So, in this calcium, it lost 2 of its electrons, right? And so that means it has 2 less electrons in its outermost shell than it should. And that means that it's now overwhelmingly positive, right? It still has the same number of protons in its nucleus. It just has less electrons. So it is an ion of calcium because it has 2 extra positive charges because it lost those electrons. Okay, same here with our chlorine, right? So in this chlorine, it has gained electrons, and so it has more of a negative charge than it should, and so it's an ion, right? So it's not just a stable number of protons matches the number of electrons. In an ion, there's a variance. Okay? Okay, so let's use sodium and chlorine to kind of emphasize this point of ionic bonding. Okay, so sodium has one valence electron in its outermost shell. It's highly reactive. It really, really wants to either get rid of this electron so that it can have a happy outermost shell, or somehow steal 7 electrons. So that's unlikely. So what's going to likely happen is it's going to get rid of that extra electron. So when it does, and it donates it to chlorine, which has 7 electrons in its valence shell. So when it gains that electron, it's going to have a full octet. It's going to be happy, right? So, and we see when that happens, when sodium donates that electron to chlorine, it actually takes 2 highly reactive atoms and it makes them into something very benign, sodium chloride, or what you know as table salt. Okay, so table salt is an ionically bonded molecule. So the only thing that is lost here, right, or that is at stake here, is that when sodium donated that electron, it made it a positive ion, right? It has more positive protons in its nucleus than it does have negative electrons in its orbitals, versus chlorine, right? So chlorine is now a negative ion because it gained an electron. So there's more electrons in its orbitals than there are protons in its nucleus. So opposites attract, and now we have table salt. Okay, so now I want to talk to you about polar and non-polar covalent bonds. Okay, so when 2 atoms of the same element are sharing electrons equally, totally fair, there's no pulling at all, it's a complete even share, that's considered a non-polar covalent bond. Okay, but when atoms of different elements share electrons, they don't have a tendency to share them evenly. Okay, they have a tendency to pull one closer to the other, and that's based on something called electronegativity. Okay, so when the electrons are not shared evenly, if the electrons are getting pulled closer to one of the atoms versus the other, then we would call that a polar covalent bond. Okay, and so that results in, because of the difference in charges on an atom. So we're going to kind of show that as an example with what with some inorganic molecules. Okay. Okay, so let's look at this oxygen atom here bonded to two hydrogens. So we see this is H2O or water, okay? Because oxygen is more electronegative than hydrogen, it will pull the shared electrons closer to oxygen. Oxygen's more of the hog, right? So when it pulls those electrons closer to it, it makes it overall more electronegative and it makes the hydrogens more positive or partially positive, okay? And so we see that with all of our three important inorganic molecules. We see this sort of polarity, okay? And so there's a really important reason for this that we're going to put a pin in. We're not going to jump in right now. I want to instead show you a little bit closer up what is happening in this electronegative pull here, okay? So essentially, with water, okay, right? The red is oxygen, the two yellows are hydrogens, okay? Uh, these electrons that they are sharing, you can see they're closer to the oxygen atom, and so it's making the oxygen overall more negative, and the hydrogen bonds overall more positive. Now, that's really, really critical to the characteristics of water because these slightly positive hydrogen bonds then interact with the slightly negative oxygen sides of the H2O molecules. So we can kind of think about why this would make for a weak attractive force between all of the water molecules. Okay. And that gives water the property that it does. So, for example, if we think it's almost like these guys are acting like Velcro towards each other. So if you had one little piece of Velcro, you're not going to be able to do very much. But if you have a whole suit made out of Velcro and you run up to a Velcro wall, you'll be able to stick to it, right? So we can kind of apply that to why these weak attractive forces between the hydrogens and the oxygens in water between molecules kind of make them like glue, stick them together. Okay. And so that weak attractive force is very, very important. This hydrogen bond is extremely important. Okay. Because if we think about how hydrogen bonds are used outside of just water, right? We can see how hydrogen bonds are used in our DNA, right? They hold together our strands of nucleotides, right? Hydrogen bonds in proteins help them give their tertiary and quaternary structures. Okay, so hydrogen bonds are really critical, okay? And so let's just take a look at this picture for just a moment so we can sort of see why these hydrogen bonds, again, give water the properties that it does. Okay, so these are weak bonds, but when they're collectively put together, it makes for this really strong pull, and it makes for this strong connection between all the water molecules because of these slight hydrogen bonds pulling. Okay, so that's why if you these little mini bits of gluing together make it so that like if you jump into water and you belly flop, you smack the water, right? Because it's kind of glued together very weakly. Okay, and that's why if you were to jump from a really tall height into the water, it could kill you because that those hydrogen bonds, even though they're pretty weak, when they're so abundant and all together, they still create a pretty strong force. Okay, that's also why, though, if you were to, instead of belly flopping, dive into the water using your fingers to break up some of that surface tension, okay, then you're able to sort of push apart those water molecules and get your body in without smacking the water, right? You've kind of broken up those hydrogen bonds by breaking the water tension. Okay, so that weak attractive force, this weak attractive force is what gives water the properties that it does. And it's also the reason that two polar molecules, they're actually stronger together, right? So, or in this case, billions of polar molecules like water are stronger together. Okay. And so this here we can see just another example of polar covalent bonds where our oxygen is having a hydrogen bond, weak attractive force with the hydrogen in the other water molecule. Okay, so this is where we are going to pause, and we're going to jump into the chemistry of water in our next video.